Welcome everyone to the new video of this Microprocessor 8085 lecture series, and in today's video we will learn about 8085 interrupts. So this is a super important topic and it's a quite tough topic to discuss. And this will be a long video, I guess. So please pay attention and keep watching. So first of all, what is an interrupt? Interrupt is, suppose you're watching this video and suddenly you get a call. So there will be a button displaying on your phone screen, right, that someone is calling you. So what will you do? You will just stop watching this video, receive that call, and then again resume the video. So what is happening? I was performing a task, some external action occurs. I need to service that task, finish it, then again resume what I was doing before. So this is called interrupt. Now this is a real life example. Within the machine, what happens? See, you know that within the machine everything is everything is done using programs. So suppose there was a program for watching a video, that if the user clicks on this button, now suppose this is a YouTube icon, then it will get opened, YouTube will get opened, choose a video, like click on that and watch your video, right? For this task there is a several program. Now for something else there will be other program. So interrupt is, if we use formal language, a special condition that arises during the working of a MUPI. It creates temporary halt during program execution. In return, MUPI services an interrupt by executing a subroutine called ISR. ISR is interrupt service routine. Basically, what does it mean? That I was doing some program, I get call from an external program, I have to go there, execute, then return and resume. Like what happens, you're watching this video, if someone calls you, you will resume the video, you will not do this, you will not start this from the beginning, right? So what are the steps that happens in interrupt? See, this was my program, okay? So this was occurring according to the addresses. Now suddenly I get an interrupt. So MUPI was executing a program as per addresses. Now interrupt occurs. MUPI needs to response. So this will, as I told you, the call instruction will come here. So whenever there is a call, I need to store my return address. This was my return address. So first, when there will be call subroutine, first I have to go, so push return address into stack, and PC will get the address of that ISR, that subroutine. Only then it will go to that subroutine and serve, right? So PC will get the ISR address, go there, execute, return. Now pop the return address from stack, go back to there, and then execute. So these are the steps that will recur to execute a subroutine, so interrupt. Okay, interrupt is also a subroutine. Now there are two types of interrupts. One is software, another is hardware. Software interrupts is when, suppose a programmer is writing a program and I need to stop what I'm doing and need to execute something else. So then he or she can write a code for that and make a software interrupt. Okay, just suppose I think I've watched in the architecture video that there are 8 software interrupts, which are RST0 to RST7, RST0, 1, 2, 3, 4, 5, 7, all 8 interrupts. So I will just write RST0. So RST stands for reset, and this particular instruction resets the whole MUPI. So if I was writing some program, I write RST0, the program stops here, it will reset the whole MUPI and then again execute. Okay, so this is an example of software interrupts. All the software interrupts means RST0 to RST7 all are on the same priority. Second is hardware interrupt. This is the main topic of discussion of in today, that the hardware interrupts. Hardware interrupts are, suppose when we are working on a PC, we connect external devices through ports, right? Suppose printer, speaker, monitor, whatever you want to. So when we connect some external device through a port, my MUPI gets interrupted. So these are the types of hardware interrupts, and you know there are 8 ports for interrupts. So there are some pins. Whenever the pin gets attached to a device, it will invoke a signal. Okay, so invoked by a signal on pins, and example is connecting external device to MUPI. There are 5 hardware interrupts: trap, RC 7.5, 6.5, 5.5 and INTR. Okay, so the priority is like this. So when a MUPI sees these hardware interrupts, it sees everything at once. I mean, just see this, and when it executes, it will execute one by one. So highest priority is, so first trap will get executed, then 7.5, 6.5, 5.5 and INTR. Okay, so now hardware interrupts, either they can be edge triggered or level triggered. I will discuss that what is edge and what is level triggering. And the next is hardware interrupts can be disabled except trap, because it is the highest priority interrupt, and this is for some special task. If some special condition occurs in your MUPI, only then trap will get executed. So trap can be disabled, but all the other interrupts I can disable them. Suppose I'm doing something important task. Suppose I'm watching this video and I don't want to get disturbed by any message or call or anything, so I will put my phone on the aeroplane mode, right? So this is so when we do airplane mode, if I like disable my, it is just example of disabling everything, disable every interrupt, so nothing will disturb me again. I will just do this task. Okay, so this is the properties of hardware interrupts. Okay, software interrupts can't be disabled. Why? Because see, software interrupts at the codes, it's a code that is written by a programmer. If you don't want to perform any interrupt, then you will just simply not write that code. So this is why disabling is not something that happens in software interrupts, because it is just invoked by the programmer. But in hardware, if you want to connect any device to any peripheral devices, then we need hardware interrupts. So this is why disabling is something that can happen there and not in software interrupts. Okay, so from these properties you can distinguish the difference between these two. This is an important question that may come in exam. Okay, so this was for software interrupts and hardware interrupts. So I've used a term called level triggered or edge triggered, right? So this happens only in signals. Triggering is, suppose this is my clock pulse, this is one clock pulse. If I just trigger this, then again this will happen. So level trigger and edge trigger is, suppose in this clock pulse, if this is my 0 and this is 1, if the signal is going on 1, then this is called, it is on a level, so this is level triggered. And when I was going from 0 to 1, this is called edge triggered. Okay, now don't forget these two names, level trigger and edge trigger. This is something important in the upcoming minutes. Okay, from now we will just deal with only hardware interrupts. So there are 5 types of interrupts. So these are the properties of the interrupts. Just listen to these properties carefully, only then we can understand the diagram later on this video. Okay, so I've already told you that trap is the interrupt that is on highest priority. So trap is on 1, RST 7 is on 2, 6.5 is on 3, 5.5 is on 4 and INTR is the last one. Okay, trigger. RST 7.5 is the only interrupt that is purely an edge triggered interrupt. These 3 will be level triggered, and trap is the most beautiful and it's the most wanted interrupt. It is facilitated with 2 possibilities, either it can be edge or level, but this one is purely edged. Okay, now SIM, I think I've already told you what is SIM and NIM. It was just only a 1-line definition, I think. we will discuss about SIM and NIM in the next video. This is just uploaded, it will be updated soon. In SIM you can see that there is the circuit is like this: M7.5, M6.5, M5.5, RST 7.5. This is not something that you want to hear, just look at this one. Okay, what is masking? Masking is basically disabling my interrupt. Like, I just don't want any interrupt to disturb me right now, so we can disable them by using the SIM instruction. Now trap, being the most important one, can't be masked, can't be enabled by anything, so this is the SIM can't be used here. But for 7.5, 6.5 and 5.5 we have SIM instruction, and for INTR bar we can't do this with SIM instruction. Okay, next is disable by DI. DI is disable interrupt. It's a dangerous instruction. Whenever you write DI, means all interrupts will get disabled except trap. Trap was originally named RST 5.5, okay, but then again, just to mention that this is important, just to make you realize the significance of this instruction, it was later named trap. So using DI, all the others can be disabled except trap. Now vector. What is a vector interrupt? See, I've already told you that all the interrupts that will occur, they are just nothing but subroutines. Now all my subroutines, whenever we write call and the program name, this is basically an address. You have to go to that address and then execute the program and then return. So in our 5 hardware interrupts, everyone has a specific address except INTR. These 4 interrupts which has a certain address is called as vector interrupt. So those interrupts who has certain addresses, they are called vector interrupts. And as INTR bar being the most ignored, it's the least prioritized interrupt, so it doesn't have any specific address, it can goes to anywhere. But these are the most important one, so they have some address, and as they have addresses, they are called the vector interrupt. So all these 4 are vector except these one. So vector interrupts, so these 4 have some unique addresses. Okay, so what are the addresses? I have written them, don't by heart them, there are a reason why they are addresses like this. Let me tell you. First, trap, which was in real RST 4.5, RST 7.5, RST 6.5, RST 5.5, RST 4.5. So 5.5 into 8 is 44. Turn this 44 into hexadecimal number. What will happen? 16, 232, 12. 12 in hexadecimal is A, B, C. So 2, then C. Look at this address. So 5.5 is 002C. Do these 6.5, 7.5 and 4.5 yourself. So this is how we can get the address of these interrupts. Okay. Before I start my diagram, I want you to know some properties. Suppose in hardware interrupts we have priorities. Okay. So if we are doing some task and suppose 2 interrupts occur, RST 7.5 and 6.5, who will get performed first? 7.5, then 6.5. So what happens, suppose this was my program RST 7.5. Okay, MUP gets his address, go to perform this, get back. In between, I have to store that in 6.5 there was some signal also. Now this signal can be continuous or can be not continuous, right? Like when we plug something in RST 6.5, this was 1, but then it go low as it was not serviced. So you might lost that something occurs in RST 6.5 and we just lost the data. the task has not been performed. Okay, so for that we need to store that, and for in this condition it is declared as pending interrupts. Okay, so the first thing you should know that it is being prioritized, and for that we have some solution also, that so that we didn't lost the another interrupts, they will get stored and they will get performed respectively. Second is, when one interrupt is being performed, all the others are disabled. Suppose this was my program call S1, this is the subroutine 1. Suppose RST 7.5 has occurred now, so this will get performed and come back. By meantime, all the others are disabled. When the subroutine gets executed and we will get returned to our original program, for that first you have to write enable interrupt also, because if you didn't write enable interrupt, all the other interrupts are still disabled, they will not get enabled by itself. MUP can't do this by itself. The programmer has to write that now enable interrupts and then go back to return and then execute some other interrupts or your program, whatever you are interested in. Why did I tell you this one? Because in a normal subroutine and in an interrupt, that is the difference. All the interrupts are subroutines, but all subroutines are not interrupts. Why? Because in a subroutine we are just doing call program, okay, go program, discuss, return. But in subroutine, call interrupts, go to interrupts, performed, enable interrupt, and then write return and come back. So this line, this instruction is the difference between a normal subroutine and an interrupt. Okay. Now the big diagram comes. Don't get scared. If you understand the properties of the 5 interrupts well, then this will be an easy diagram for you. So what is it? This is the circuit, design of the circuit, which is originally on the chip. Okay, so we need to know how this functions. So in the chip, they are being prioritized, they are situated like this: 2, 3, 4, 1 and 5. What is on 2? RST 7.5, 3, 6.5, 4, 5.5, 1 is trap, and the next one is INTR. Okay, so first one is triggered. As you can see, 2 is edge triggered, so this is why the signal is like this. 3, 4 is 3 and 4 is level triggered, so they are like this. 1 is trap, it can be either edge or level, so both. And 5 is level triggered, so it is like this. Now this thing come. Okay, this flip-flop will, you have to write, you have to draw the diagram here also and here also. I didn't do this just because then the whole diagram will become too untidy. For trap, it just have to occur and it will just get executed. It doesn't need any other conditions and something. We just need the signal from trap. Next is INTR. It doesn't have any flip-flop, just because it is not that important. It is the least prioritized interrupt, so this can happen later also, so this is why we don't use any flip-flops here. I will just discuss how this first functions. Suppose RST 7.5 signal has came. This is my D flip-flop. Do you know why D flip-flops are used? It is used for storing 1 bit. So my D flip-flop, suppose this is here, you should write the D. This is D. Now this signal goes on. 1 came here, it will get stored. This is Q. Q will produce 1. Means I have some signal in RST 7.5. This goes on, so I'm producing 1 only here. Now if you want this interrupt to get executed, first you have to go through this gate. This is an AND gate, If this AND gate also gives you 1, then what will happen? Call 003C. What is 003C? It is the address of RST 7.5 subroutine. Okay. So this gates need to get, this gate have to give you the result 1 to get this address and perform my interrupt. But there are other signals also, as you can see. What are the signals? First, M7.5. Do you remember this one? I've done this in SEAM box. In SEAM instruction, there is a mask 7.5 option. If I mask this one, means if this is 1, means this interrupt can't get performed. So if it is 1, this will come. Now this is AND gate. This will give 1 only if all the inputs are 1. But if it is 1, my interrupts get executed, so I can't give 1 in this input line. This is why there is a bubble, which is like which works as a NOT gate. So when mask is enabled, then this will give you 1, this will goes as 0, and it will give you result 0. But if I want to execute this, it is 0, so this will become 1, and I will get my result. For that also I need to make the other signal also 1, but for these two I think you understood what are the conditions. The next signal, as you can see, is common for every other gate. Is this one, this one, this one, this one. In trap, there isn't something gate, because I told you that tap is the most important one. So if you want to execute tap, it just have to get the signal and it will get executed. Call 0024. But for the others, you have some certain conditions. Now, what is the common signal that is going in all these gates? Let us see this. This is a SR flip-flop. Let me draw this. The name is INTEFF flip-flop, which is a SR1. Now what is SR? Set and reset flip-flop, right? This flip-flop will produce this signal. What happens within this flip-flop? If you want to execute the interrupts, I have to produce 1 in this signal. If I want to produce 1 from this flip-flop, I have to set this input. So for setting, what instruction do we use? Enable interrupts, right? Now think that you don't want any of your instructions to work, interrupts to work. Then what will you have to do? You have to disable everyone. For disabling, just you have to pass 0 in this line and everyone will get disabled except tap. For that, we have also another option, which is resetting. But for resetting means disabling all your interrupts, we need some conditions also. So for resetting, there will be an OR gate. What is the function of the OR gate? If any of the if any of the inputs are 1, then it will produce 1. If all of them are 1, then it's like Sone pe suhaga. But if any of them is also 1, it will reset everything and disable all your interrupts. So what are the conditions that can reset this? 3 conditions are there. 1. DI. What is DI? Disable interrupt. If I use this interrupt at any point in my program, this will disable all the interrupts. This is the power of this instruction. So if it is 1 means DI, if DI is produced, then R will get 1. If R is 1, mean reset, it will reset all, like it will produce reset signal and all of them will get disabled. Okay. Second condition is, suppose when we restart your machine, for a particular amount of time, you can't perform anything on your computer, you can't do any task. For a particular amount of time, when the operating system is get loaded from secondary to primary memory, within that scope of time, nothing can be performed. Neither programs, neither interrupts, not anything. So when your system is getting reset, so your system resets, then also not anything will work. What is the third one? The third one is something that I've already discussed. If any interrupt is already working, any interrupt recognized. Okay, pardon me for my handwriting. What is this? Suppose I was performing something, RST 6.5 has occurred. Call subroutine, perform, enable interrupt, then return, go back to your return address. In between these, while I was performing this, suppose RST 7.5 has occurred. This has the most, this is higher priority than 6.5. So what will happen? Do you think that within the beach mein the 7.5 will get occurred? The 7.5 will get executed? No. First RST 6.5 will get executed, enable interrupt, only then after returning to the original program, then it will go to RST 7.5. But when any program is getting, any interrupt is getting executed, meanwhile not any interrupt will get performed. Okay, so this is the third condition that is required if you want to disable any interrupts. So this is a INTE flip-flop, SR flip-flop. If you want to produce one for everyone, like you are ready to execute any interrupts that will occur. So for that you can do enable interrupt, it will get set and it will produce one to everyone, and if all the inputs are 1 in my AND gate, it will produce 1. Okay, but if you want to reset it, just fulfill any of these conditions or all the conditions, whatever you want, it will get executed. Okay, so I hope you understand this part. Now go to this one. But before this one, no, okay, just let me first discuss this one. Wait, I've already told you about this flip-flop, that what the actual task of this, but let me describe in detail. Suppose I'm performing any task and RST 6.5, 5.5 and trap is the most important. I shouldn't give any example of this, and INTR. Okay, all these three interrupts occur according to importance. First interrupt that will be served is this, second is this, third is this. When one is get performed, I don't want to lose the data of these two, right? So you need to store them. To store that, okay, there is some signal, I need to store that. I have some there was some producing signal. We have to, the MUP perform, you should perform these interrupt first, but then don't forget these two, later on perform them also. So what will happen, I'm sorry that I'm fumbling a little bit. RST 6.5, when it is being performed, suppose these two signals, they may be continuous or they may be not continuous. This had to get stored. These are pending interrupts. What will happen? Suppose in 6.5, this is my D flip-flop. Why D flip-flops are used? To store 1 bit. Signal occur here. This goes 1. D gets 1. It stores and shows that 1. Now my signal goes low, so this will become 0 now. But as it stores the data, K will still give me 1. Means it will remind the MUP, hey, though it is 0 here, but still I'm producing 1. Means probably at some time there was 1 here also. and you lost the data, maybe because you are performing some other maybe you're performing some anything else operation, something or something. So what you have to do, that MUP, you have to go check whether 6.5 has something to execute, then execute and make this clear. What is the task of this D flip-flop here? It will just remind the MUP that you may have some interrupts, but you are busy, so you have lost that signal. But I have stored that okay, you have something, you have to go check there and execute. Okay, so what would happen? I'm just giving this example. Okay, so it's RST 7.5. This signal gives you 1. You store the value, get 1, gets performed. But in some case MUP is busy, this goes as 0, but this is still 1. So okay, now the MUP performed this operation, go back, and then MUP see that though this is 0, this is producing 1. So now MUP will go check RST 7.5 and perform some operation. After RST 7.5 interrupts get executed, now this should also go to 0. But from this point, when your task gets executed, if you want to show 1 to 0, means now RST 7.5 is free again, you have to clear that D flip-flop. D, Q, FF, clear. Okay, you need this. You have to use this clear instruction to make this one 0. For clear instruction, again we have a gate, which is a OR gate. There are 2 conditions. Now remember this one very carefully. Only in case of RST 7.5 there are these 2 conditions. For the other 2 there will be only 1. Not anything written as RST. I think you can see there is something called reset 7.5. This reset 7.5 is only for 7.5. Okay, for the other 2 scenarios there will nothing called as reset 7.5. This is only RST recognized. So what happens actually here, let me draw this. See, suppose my task is being performed, so I want to make this 0. So one condition will be if RST is recognized. Okay, I've done this. So now clear my instruction. Okay, this is one way of clearing it. What is the other way? And why is the other way? If I saw that my RST is recognized, you should make it 0, right? But I think if you remember, RST 7.5 is the only interrupt which is purely edge triggered. 7.5. So the special condition RST 7.5, why is there something called reset 7.5 also in this OR gate? Because of this edge triggered. Why? Thought that you are doing some program and you don't want to get disturbed, so you disable all your interrupts. Now you have performed your program. Now I want to show what are the interrupts that has occurred in that time when I was busy in my program. So my program ends and now I enable my interrupts. All the interrupts will, if there was any interrupts that come, all of them will come one by one. They all want to execute at once. Obviously they will get executed by an order, by priority, but all of them will come. Suppose RST 7.5, trap, INTR 5.5, all these 4 interrupts occur in that time. When my program gets executed, obviously trap will get executed. It doesn't care whether you're doing a program or something, as it is the most important one. It will happen during any program. Then who gets the priority then? 1, 2 and then 3. But see, in these 2 cases, this flip-flop, when this will just show this is 1 and this will go 1 to 0 and this is 1. In this case, the MUP will see that this is just 1. It will just see that this is 1. it is a level triggered interrupt. Whenever MUP sees this is 1, it will not hesitate to perform this interrupt. But in case of RST 7.5, as it is a edge triggered interrupt, I need to see that action taking place from 0 to 1. This is why in sim instruction there is an other button which is RST 7.5. So when we do RST 7.5, suppose when I was busy in my programs, all those signals were coming and now I want to execute all those interrupts. So for them, when we will execute them, suppose I didn't still recognize that this operation occurs, so I want to make this one as 1, only then this will get clear and I will get 1 from 0. If this is not recognized, I want to make this condition true. For that I will do a reset, and when we will do reset means now my RST will again go from 0 to 1, or like it wasn't a continuous signal, so it will just go from 0 to 1, 0 to 1, 0 to 1, 0 to 1, and it will show the MUP that see I am a level triggered, I am been reset now. If I send 1 now, do clear this instruction and tell the MUP that, like, show that now this instructions also get performed. Okay, so what happens in these programs, in these interrupts, I think this one is clear now. And for these 3, the D flip-flop is used, trap is obviously not used. And for INTR, see this INTR instruction, I am not discussing this in detail because in 8259 PIC I have to discuss this in really broad way. So this is why, see, if INTR occurs, then it has to first, if the signal is enabled and if the common signal is also enabled, then it will get its address and the random address. But for these 4, all these 3 instruction has to be fulfilled, and for them I'll told you what are the conditions. Okay, and this reset 7.5 is just for specially RST 7.5, so that while resetting it can show that level trigger, the edge triggering. For them, first of all it has to show if it is 1 then go to 0, but it's still producing 1. Just you have to get and perform. It is as it is a edge triggered interrupts. So if the MUP see that there was 1 to 0 suppose, but it's still producing 1, then it means I have to go and execute. But in case of RST 7.5 I have to reset so that it will again go to 0 to 1. So just for edge triggering, this special condition is there, and these 2 are all of them, these 2 are level triggered, so this is why this special condition is not there, otherwise all of them are same. And the last part is the addresses, and so this is a bit untidy, just a second. Okay, so for trap this is the address, for RST 7.5 this is the address, 6.5, 7.5, and in case of get ISR address, sorry, in case of INTR, the device had to specify that in which address you want to go, in which port you are plugging in. So when this goes 1, get ISR address from your device. And now what are the addresses? See, it could be any of the software interrupts also, from RST 0 to RST 7. So this is why, just to make this on a order, I have written this. So 0001 is for RST 0, 0008 for RST 1, then 8, then +8 and all that. I'm really sorry. Okay, so just by these addresses, then 0028 284, it's 28 3038. Just for maintain this order, I've written them. Don't bother. This will produce any other address and your interrupt gets executed. So please be specific for these call 0024, 26, 34 and 3C only, and for this randomly addresses will get executed, so don't get bothered by these some not important addresses. Okay, so this was your interrupt circuit. I know that this was a little bit trickier one, so if you have any problem, please ask me in the comment section. For notes you can mail me, and thanks for watching. Thank you.